So let's start with a sample, XY sample. And we make it bigger. Let's see. So we're going to start with an XY sample. I'll just have X to be sequence 1, 2, 6. In other words, X is equal to 1, 2, 3, 4, 5, 6. And Y, the true model, X is 0.98 times X plus 1.2. Good. So that is our true model. And certainly we need to add noise to it. So going to do random noise, mean 0, standard deviation 1. Good. Let's set a seed. So that we all get the same answer. 8829. Let's quickly plot this. So we're going to plot X, Y, and from our, you should know, PCH. Let's pick 19 and main transport X lab is X and Y lab is Y. Hopefully it will let me plot this. Should. Source. Do we get a plot of that sort? We have the simple plot here, and going to set the limits for the X and Y axis. And that's what I would have. I can't see. I just want to get a nice visual. So that is our answer. We have the 6 points. Sort of random, make it more random, but good enough for that. How do we fit a line for this stuff?
With R.
With R.
Is there a command for it?
There is a command.
Okay.
So we want to do the line of best fit or least squares regression. Simple LM. LM stands for linear model. Y tilde X. Both Y as well as X are in the environment itself. So that's good enough. So I'll call that the mode. Good. To get the fitted values from the model, we can use mod dollar fitted values, which is going to pull up the fitted values from the object mod. So I can add the fitted values y hat to the existing plot using the lines command or function actually. So lines x value comma y value, excuse me, mod dot fit not y value, comma, going to use red. So let's see what happens. That is the fitted value, right? So we are going to make inference based on that single line. Bayesian statistics is going to differ in that regard. I'll show you how. So we have y hat equals beta 1 hat x plus beta naught hat. The true model, if we go back and look at it, the true model is y equals 0.98x plus 1.2 plus, I'm adding noise, right? So true beta 1, true beta naught, multiplied by noise, I'll call it epsilon. That epsilon is distributed as a normal 0, 1. Do we agree? So the true value of beta naught is 1.2. True value of beta 1 is 0.98. Of course, we don't know the true model, which is why we collected this sample, and the sample gives us the model. Yes, the fit, the line of best fit. If I change these parameters, for example, if I change these beta 1 values and beta naught values and the epsilon values in some way, the reason being, if the noise follows a normal distribution, y hat is going to have a normal distribution with mean beta 1 hat x plus beta naught hat. I initially had the variance to be 1. I'm going to let it be 1. I'm not going to change that value. So, so the mean is beta 1 hat x plus beta naught hat. The variance is just 1. It is a non-parameter. In practice, though, I could treat 1 to be some s and or sigma and try to estimate that also. What I'm trying to do here is rather come up with different choices of beta values and produce different lines. So what is one way of doing that? Let's say going to simulate I have to use a loop to simulate this. Beta 1 hat and beta naught hat are not just single values in Bayesian, rather beta 1 is going to have a distribution, beta naught is going to have a distribution. So this is what I'm going to do. I'm going to run, say, 100 simulations. Hypothetically, let me assume that the prior distribution of beta 1 hat, or not prior, the posterior, we will do this in a detailed manner later on, but I'm just trying to show you the fundamentals. So the posterior of beta 1, let's call that normally distributed. Let's use the mean or the model fit for the coefficients. The estimated values for beta 1 hat and beta naught hat would be 1.233 and 0.394. So I'm going to assume the posterior of beta 1 hat is distributed with mean 1.233 and a standard deviation of 0.1. And the posterior of beta naught it's normal 0.394, mean and standard deviation. Let me just hypothetically use 0.05. Mind you, in practice, our objective is to come up with these two distributions. I'm just trying to show you the basics of Bayesian statistics. So I'm using hypothetical posteriors for beta 1 and beta naught.
So you got a prediction for beta 1 and beta naught from just a regular model.
But
and then that distribution you're just kind of pretending you got from the posterior.
yeah, exactly. I mean, even that I am pretending that I got it from the posterior.
Yeah.
So, but what I'm trying to say, I picked these two because it's easier. But when you use a prior, you end up getting a posterior, and somehow I estimated these values. In practice, we have to simulate and sample. So K and 1, 2, and sim. So 100 times
And dot sim.
n dot sim. Thank you. I'm going to randomly sample beta 1 and beta naught. So it is from normal. So if I took a random sample, oops. Generating a single observation. The mean is 1.233. Standard deviation is 0.1. Beta naught posterior distribution 1. Mean is 0.394. Standard deviation 0.05. these parameters have to be estimated in some way. I'm going to save these beta values also for good measure. So saved beta 1, I've saved beta 0 using, or I am saving using those two arrays or vectors, initialize beta 1 and beta 0.
You just initialize them in like a chain like that?
Huh?
Yeah. Just initialize them in a chain?
Yes.
Thanks.
I didn't do that in context because I didn't want to confuse them. You can actually have quite a lengthy chain and keep all deciding. So we have those two values. Now I'm going to come up with a y-hat, the Bayesian version. Going to take beta 1 that was simulated, or beta underscore 1, multiply that by x, and beta 0, the one that got simulated. This fitted values that I'm simulating as a distribution. I'm assuming the posterior distributions to have a standard deviation of 0.1, 0.25. Theoretically, the mean is this for y-hat, the standard deviation. I'm assuming it to be known, but you can vary that parameter also. In other words, you can come up with a posterior for beta 1, a posterior for beta 0, posterior for sigma or sigma squared. So now that I have y-hat, I'm going to add lines x, y, or y-hat actually, and I'm going to pick random. We'll just pick one color. What should we pick? Something that will contrast that nicely. Then all this much. We will see. Gray or GB. So I'm changing color so that we can see this better. Max color one. Reduce this further. Put it at 60. Okay, that's good enough, yes. So instead of making an inference just by using that single line, I'm going to make an inference using all of those lines. Does that make sense? So even though we call this the line of best fit, statistical theory from a frequentist approach would simply dictate, okay, I have that line and I'm going to have a fixed upper and lower bound for beta 0 and beta 1. But here we're going to vary beta 1, beta 1 hat and beta 0 hat. So I'll get different lines. How do we know that we are fitting a proper model? getting a proper model as long as all data points fall within the bounds that we have, or bounds that we come up with in posterior prediction. Does that make sense? So do all of the points fall in that range? Yes. Now, how do we mess this model up? We can actually mess it up and not have a good model. All I have to do is change the estimated posterior distribution. Let's say hypothetically I use the prior, and the prior ended up giving me some weird so some weird posterior that I get using a prior, none of these data points fall within the different lines that we have. So clearly, this estimated posterior distribution is no good, neither for beta 1 nor for beta 0. Let's go back. What did I have? 1.233 and 0.394. Of course, I'll get the same one because I set a seed. Okay, let's say what distribution I am going to get for beta 1 and beta 0. Mind you, here I'm simulating random numbers to do that posterior prediction check. What does the distribution of beta 1 look like? Well, the distribution of beta 1 is normal. So if I simulated different betas, if I kept on simulating different betas from that distribution, I will end up getting something like that. It's not that great because we don't have enough beta values. So those are the beta values that we simulated, and I'm just plotting those beta values, and that is the density of beta 1. Likewise, we could do for beta 0 using the same values. And that is also normal. Not getting a proper distribution because I don't have enough simulations. If I increase the number of simulations, I will get more a nicer picture. Let's see. Perhaps I'll do 256. Much better, right? So here, that is our posterior distribution, and the different beta values that you get for or beta 0 values that you get over here within 95% will form the 95% credible interval for beta 0. A similar manner, whatever that I get for beta 1. Whatever that falls within 2 standard deviation or whatever will be a credible interval for beta 1. Does that make sense?